previously covered the kind of bonds that form between a metal and a non-metal, and between two non-metal atoms. What about when a metal and a metal are bonded together? Well, they don't actually form any kind of chemical bond. If they're two different metals, they form something called an alloy. And if we're talking about a pure metal, such as iron or copper, the atoms in that are held together by a metallic bond. To understand a metallic bond, it helps to understand the formation of ions again. We've previously mentioned that metals form positive ions if they're forming an ionic bond with a non-metal. Great, they can give their electron to the non-metal, who will then form a negative ion, while the metal forms a positive ion, and they'll form a bond, an ionic bond. What if the only other atoms that are around are other metal atoms? Well, they're all going to want to form positive ions. And they form positive ions by kicking out their electrons. Those electrons have got nowhere to go. So they actually form a discrete, separate entity to the positive ions, the metal ions. And we say that the electrons have become delocalized. That is a key word, delocalized. What that means is they're not stuck to any one atom. For example, what we've got here is what a metallic structure would look like. It's many positive ions, metal positive ions, metallic ions, in these layers here. And then we've got the negative electrons, so we've got the electrons here, surrounding those positive ions. They can move all the way around wherever they want to go. So this electron here can go to here, can go to here, can go to here. If you picture a piece of metal, an electron can move anywhere it wants around the metal. It doesn't live around one particular atom anymore. And the word for that, as I said, is delocalized. It's often described as a sea of electrons with like little islands of positive ions in there. It's all stuck together by the electrostatic attraction, there's that word, electrostatic attraction, between the positive ions and the delocalized background sea of electrons. So this positive sticks to this negative, because two positives next to each other won't stick to each other, so they have to stick to the background electrons. This makes metals very strong, but it also gives rise to some typical properties of metals. So for example, they're excellent conductors of electricity. That's what defines metals, because these electrons are free to move wherever they want to go. If you set up a potential difference, a voltage, they're all going to move one way or the other together. So that's going to conduct electricity. Same goes for being malleable. They're malleable because the ions are not stuck to each other, they're stuck to the background sea of electrons. So if I give it a push, or if I try to bend it, then the layers of ions will move around, but they'll stay stuck to this free-flowing background delocalized sea of electrons, meaning that metals are very malleable. They're very ductile for the same reasons. They're great conductors of heat and electricity, and it also gives rise to the properties of alloys, which are, as I said at the beginning, mixtures of different metals. It changes the properties of from being a pure metal to being an alloy, and it means that an alloy is actually a mixture, not a compound. We can look at alloys in a later video. Alright, so that's the bonding in metals. Thanks for watching.